Assalamualaikum and hi class. We are still in the topic of haloalkane, but this is the last mechanism that you have to know, which is SN1 and SN2. Let me introduce you what is SN2 and what is SN1. SN2 is bimolecular nucleophilic substitution, while SN1 is unimolecular nucleophilic substitution. For SN2, the reactivity of haloalkane is methyl haloalkane is most reactive toward SN2 mechanism, followed by primary, followed by secondary, while tertiary haloalkane is unsuitable to undergo the SN2 mechanism. While for SN1, tertiary haloalkane is most reactive toward SN1 mechanism, followed by secondary haloalkane, followed by primary haloalkane, and methyl haloalkane are unlikely to choose SN1 mechanism. Before we go further to the SN1 and SN2, you have to know some types of strong nucleophile and weak nucleophile. This is example of strong nucleophile. For example, is OH minus. OH minus of strong nucleophile mostly come from the strong base. For example, it come from NaOH, KOH. So this will produce the strong nucleophile OH minus. Also have alkoxide ion, which come from the salt. For example, sodium methoxide. This OCH3 minus is an alkoxide ion and it will consider as strong nucleophile. Other example is Cn minus, which mostly come from KCN or NaCN. This is an example of weak nucleophile, H2O, alcohol, for example, CH3OH, methanol, ammonia, and also ethoxide ion. Alright class, we will start with SN2 mechanism, which is bimolecular nucleophilic substitution. It is said to be bimolecular nucleophilic substitution because the first step involves two molecules, which are haloalkane and also the nucleophile. So the word bi here refer to two species involved in the first step. It is also the second order of kinetics. So when we write the rate law, we will write it as rate equal to K concentration of Rx or haloalkane times concentration of nucleophile to the power of 1. So the overall order is 1 plus 1 equal to 2. So it will be second order. Third characters of SN2 mechanism is it only has one step mechanism, it has a transition state, and no carbocation ion rearrangement. I will show you later what actually happened in SN2 mechanism. And all SN2 reaction proceed with backside attack, resulting in an inversion of configuration at the electrophilic of carbon atom. Alright class, when you want to outline the SN2 mechanism, it is very important for you to have your nucleophile and also your haloalkane being written like this, in this 3D shape. Maksudnya, awak punya haloalkane mesti dalam keadaan 3D macam ini. CX bond mendata macam ini and the other 3 bonds backward. Ada sebab dia, you have to draw your haloalkane like this because look at the last point here. SN2 reaction proceed with backside attack. Okay, maksud backside attack, okay, I will show to you later. Okay, now, when you already write your haloalkane like this and also you have write your nucleophile. So this is nucleophile, this is haloalkane. We know that C here will become partially positive. It is bonded to more electronegative halogen, so X here become partially negative. We will show the backside attack of nucleophile toward this carbon. When the nucleophile attack the carbon here, the CX bond will break. And this step is considered as slow step or rate determining step. This first step will be used to determine the rate of reaction. After the attacking of nucleophile toward the carbon here and the CX bond break, it will form the transition state. What will happen at this state is C and nucleophile bond is formed while CX bond is breaking. So this formation and breaking of bond occur at the same time. And it is a temporary species. That's why we put the bracket here. If you can see, we put the bracket here and also the symbol double plus here to show that it is in transition state. And at the transition state, it will occur very fast when the carbon and nucleophile bond has permanently formed. So it will form a product, and the X here, when the breaking of CS bond has completed, X minus will be your leaving group. So it is generally how the SN2 occur. One more thing that you have to consider is the product here must be drawn in the inversion configuration. What is meant by inversion configuration? After the attacking of nucleophile, it seems like this nucleophile pushed these 3 bonds, so it will be in inversion of configuration like this. Macam payung awak, asalnya dia terbuka ke arah sini dan ada angin kuat, dia tolak payung awak dah ke depan macam ini. So same goes to this product. Your 3 bond here yang tak involve dalam mechanism tadi, dia akan bertukar arah ke arah sana. And your nucleophile that baru form bond dengan carbon will be right di sebelah the other side pula berbanding dengan haloalkane yang asal. Okay, boleh dapat kelas? So dalam SN2, it's more to draw the 3D shape. Itu sangat penting sebab dia melibatkan configuration. Okay, now we look at the example. So I have the hydroxide ion as my nucleophile and also the chloromethane as my haloalkane. So daripada sini kita tahu dia adalah primary haloalkane and methyl haloalkane is reactive toward the SN2 mechanism. So that's why I will draw the methyl haloalkane in this shape because I want to outline the SN2 mechanism. So CCl bond saya akan tunjuk dia macam ni, and what will occur at the first step is this nucleophile do the backside attack toward this carbon that makes the CCl bond break, and it involves a slow step to form the transition state. So what happened at transition state? Formation of COH bond and breaking of CCl bond occur at the same time, and you have to put the symbol of transition state at this state and also with this bracket to show that it is an intermediate species and it is only temporary species before it form product. When the breaking and forming bond has completed and it is happened very fast, so you will have this product, but in the inversion configuration, the COH bond and the 3 bond that does not involve in the mechanism will be drawn at the other side. So we call it as inversion configuration. So it will be our product. And we will have our Cl minus as our leaving group. Alright, so now we go to the SN1 mechanism, or the name is unimolecular nucleophilic substitution. Why unimolecular? Because the first step involves only one molecule, which is the haloalkane. So it is first order kinetics. For example, I have this tertiary haloalkane reacted with H2O to produce this product. So the rate law, I will write it as rate equal to K concentration of haloalkane. Rate determining step only involve the haloalkane. That's why the rate only depend on concentration of haloalkane and the overall order is first order. It means that only the haloalkane involved in the step that control reaction rate. That's why the name is unimolecular. And this SN1 involve two-step mechanisms. The first step is a slow ionization to form a carbocation ion as an intermediate. The second step is a fast attack on the carbocation ion by nucleophile. Okay, I will show you more detail about the SN1 mechanism. For example, this haloalkane, we know that it is tertiary haloalkane. So it will reactive toward SN1, reacted with H2O, weak nucleophile, to form this product. So let's look at the mechanism. Step 1 is formation of carbocation ion. So what will happen at the first step is this CBr bond will break. CBr bond will break, and at this step, it does not involve the nucleophile yet. It just involves the haloalkane only. So this is a slow step and it is rate determining step. So after the CBr bond break, it will produce carbocation ion and bromide ion. So it has already separate between this carbocation ion and the halide ion. So step 2 is reaction of carbocation ion with nucleophile. So our carbocation ion, which is tertiary carbocation ion, it is already stable. And there is nucleophile that will attack the carbocation ion. So it happened very fast, and as it is weak nucleophile, so H2O will be attached to this carbocation ion. Now it is as protonated alcohol, and we need to remove this H. So the H2O will involve in this step. It will attack the H, or it will deprotonate the hydrogen, and this OH bond will break. So 2 electron will go to the O, and we will have our product plus H3O plus as our side product. Can you understand about the SN1 mechanism? Hopefully you can see clearly how is the difference between SN1 and SN2 mechanism. Because after this, I will explain to you another important things in this mechanism, which is about the steric hindrance or steric effect. Now I want you to look at this diagram. Let's say the red one is the halogen. Say this is Cl. This black one is the carbon that bonded to the halogen, and this is hydrogen. Compared to this compound, this diagram, the red one is the halogen, which is bonded to the carbon, and we have the alkyl group attached to the carbon that is bonded to the halogen. So now class, I want to show you here is about the steric hindrance. Steric hindrance is caused by bulky alkyl groups makes nucleophilic attack from the backside more difficult, and they slow the reaction rate. Okay, for this first diagram, we can clearly see the carbon that attached to the halogen. So the nucleophile can easily do the backside attack. Compared to the second diagram, the carbon that attached to the halogen is hindered by the bulky group that attached to it. So for the second diagram, it is difficult for the nucleophile to do the backside attack. That's why the nucleophile attack is impossible, while for the first diagram, nucleophile attack is possible or easy. So when the backside attack is very easy, so for this compound, it can easily undergo SN2 mechanism, while for this compound, it is impossible to undergo SN2, so it will choose SN1 mechanism. Alright class, I want you to understand more about the steric hindrance, so I use this example to show you how actually it happened. So let's look at this structure. If we can see, this is secondary haloalkane, and if we react with the strong nucleophile, so it will prefer to undergo SN2 reaction. But class, if we look at the neighboring carbon, we have two neighbors here. The first neighboring carbon as primary carbon, the second neighboring carbon is tertiary carbon. So this carbon is more stable than this carbon, so it will have possibility to undergo rearrangement reaction to form more stable carbocation ion. Or in other way, we can say that this carbon is hindered by this bulky group of alkyl group, so that it cannot do, the nucleophile cannot do the backside attack toward this secondary carbon. So the reaction that will occur between this haloalkane is not the SN2 mechanism, but it will prefer to undergo SN1 mechanism because of the steric effect. So we have to do the first step, which is the formation of carboxyl ion. CBr bond will break to form the carboxyl ion, but at first it is a secondary carboxyl ion, but the neighboring carbon is tertiary carboxyl ion. So automatically it will occur the 1,2 hydride shift to form more stable carboxyl ion, which is tertiary carboxyl ion, and then the nucleophile will attack the tertiary carboxyl ion to form a product. So it is your major product as it comes from the more stable carboxyl ion. Alright class, this is the comparison between the SN1 and SN2. So you can see that first we can differ these two mechanisms by rate. The SN1 has rate equal to KRX as it is first order reaction, while SN2 is rate equal to K concentration of Rx times to the power of 1 times concentration of nucleophile to the power of 1, and the overall order is second order reaction. Reactivity of haloalkane for SN1, tertiary haloalkane is more reactive to SN1, followed by secondary, followed by primary, and methyl haloalkane are unlikely to choose the SN1, while for SN2, methyl haloalkane is most reactive to SN2, followed by primary, followed by secondary, while tertiary haloalkane is unsuitable to undergo SN2 mechanism. Effect of nucleophile for SN1, nucleophile strength are unimportant, so either strong or weak nucleophile can undergo SN1 mechanism, while for SN2, strong nucleophile are required, usually a species with negative charge. Intermediate for SN1 is carboxyl ion, while for SN2 is transition state as intermediate. As SN1 is carboxyl ion intermediate, so it may occur to form so the rearrangement may occur to form a stable carboxyl ion, while for SN2, as it has transition state as intermediate, so rearrangement is impossible. Alright class, this is the flowchart that you can use to determine either your haloalkane undergoes SN1 or SN2. Let me explain to you. First, you look at the type of haloalkane or class of haloalkane. If your haloalkane is primary haloalkane, and if it is possible to do rearrangement, means that you see your neighboring carbon. If your neighboring carbon is more stable than the carbon that attached to the halogen, so the rearrangement might occur. So it will not undergo SN2, it will undergo SN1. Primary haloalkane, so and the neighboring carbon is secondary, or it is primary haloalkane and the neighboring carbon is tertiary carbon, so means that steric effect exists, and because of the bulky group of the alkyl group, so it will go SN1. If it is secondary haloalkane and it is possible to have rearrangement, means that the neighboring carbon is more stable than it, so it will undergo SN1. And if it has no possibility to undergo rearrangement, it will undergo SN1 if the nucleophile use is weak, and it will undergo SN2 if nucleophile use is strong nucleophile. And if it is tertiary haloalkane, it will occur SN1 reaction. So hopefully you can understand about SN1 and SN2 mechanism, and try to do exercise that I already attached to you in the Google Classroom, so that you can practice and understand more about this mechanism. Okay, thank you class.